Welcome to this video tutorial on solving a problem using molar enthalpies. Let's look at the problem I have here. I want to determine the amount of heat that's released when 50 grams of octane undergoes complete combustion, given that the heat of combustion is negative 5,470.2 kilojoules per mole, and here is the unbalanced chemical equation. Now, before moving any further, let's first balance the chemical equation. So here is our simple whole number ratio. 2 octane molecules will react with 25 water molecules to produce 18 waters and 16 carbon dioxides. Let's start off by looking at this enthalpy of combustion. Recall that the negative sign indicates an exothermic reaction. So when this chemical reaction occurs, 5,470.2 kilojoules of energy is released per mole. But per mole of what? In all molar enthalpies, that mole amount is referencing one of the chemicals in the equation. In the case of a heat of combustion, that molar enthalpy is per mole of the fuel, in this case, octane. Now, when I balance the chemical equation, I end up with 2 octane molecules, or 2 moles of octane. But I'm given an enthalpy of combustion that's written per mole, per 1 mole of octane. Because molar enthalpies are always given as per mole of a substance, it's often handy to balance the chemical equation so that the reference substance, in this case octane, has a set value of 1 as its coefficient. So let's do that right now. I have 2 octane, so if I divide every coefficient by 2, that's going to rewrite the coefficient in front of octane as a 1, but maintain the balanced chemical equation because I've done the same change to all of these. So let's rewrite that now. Now you look at this equation and there might be a red flag and you say, well, I learned back in grade 9, grade 10 that you can't have a fraction in a balanced chemical equation because you can't have 25 over 2 oxygen molecules. That implies half an oxygen molecule, and oxygen molecules are entire units. You can't have half of an oxygen molecule. Well, that's true if we're talking about individual atoms and molecules. But you know now that the balanced chemical equation also gives us the molar coefficient. And it is totally reasonable to talk about 25 over 2 or 12.5 moles of oxygen. Okay? That's not a fractional amount of oxygen molecules. That is just a specific number of moles. So rather than thinking of this equation as individual atoms and molecules, let's just start thinking of these coefficients as referring to the moles of the substance. 1 mole of octane will react with 25 over 2 moles of oxygen to produce 9 moles of water and 8 moles of carbon dioxide. Let's now find the answer to our question. I'm given that I have a mass of 50 grams of octane. Now, in order to find the heat exchanged, we're going to be talking about moles of octane. So let's first convert this into moles. If I have 50 grams of octane, that means I'm reacting 0.439 moles of octane. Here's the general form of equation where we want to find the enthalpy change of a specific reaction given the molar enthalpy. The enthalpy change here is going to be equal to the number of moles that we have multiplied by the molar enthalpy. And recall that our symbol for molar enthalpies are the delta H with a subscript X. In this case, it's the enthalpy of combustion. We get an answer of negative 2399.2 kilojoules. Should always check to see whether that makes sense. 1 mole of octane produces 5,470 kilojoules. We have less than 1 mole, a little less than half, and our energy value there is lower than the molar enthalpy. So that makes intuitive sense. Let's write this out as a final statement. So therefore, 2,399.2 kilojoules of energy is produced when 50 grams of octane react. Note that when I wrote it as a statement and I used the word produced, I dropped the negative sign because the negative sign for an enthalpy change refers to an exothermic reaction where energy is produced. So when we write the word produced, that is doing the same thing as writing that negative sign.